All right, so paper number 1 that you need to be aware of is our Unit 6 Triangle Similarity assignment sheet. That's also posted on Schoology for you to be aware of what's going on. You had the key for the coordinate practice, and that was just a big review of distance, midpoint, and slope. You can look over there and see those 3 formulas. Those are the big 3 for geometry. I'm going to assume basically from this point onward that you will have find distance, midpoint, and slope of points on the coordinate plane. If you're in the position where you're like, I still don't get it, or I didn't do the homework, I need more practice, then I'm going to count on you making good use of before school, after school, or stinger to touch base with me. As far as I'm concerned, anytime I ask you to find the distance, midpoint, or slope, you're like, that's old news, I got that, no problem. Thumbs up if that makes sense to you. Okay, I'm not checking that homework, the sub didn't collect it, but you got the feedback. If you're sitting there thinking, oh, maybe I might need a little bit more feedback, or I might need, because actually doing the, I have those keys that were your warm-up, so you're welcome to come get distance, midpoint, slope on the coordinate plane, or with the ordered pairs. That's it for that conversation. Next up, the sub was supposed to do with you 6-1, and 6-1 consisted of 3 pieces of paper. One was a skills review, which was a warm-up for you, and there was a video that walked you through things like solving proportions, simplifying radicals, and a little bit of unit conversion conversations. My video stopped at the factoring because that's one of those Algebra 1 skills that non-COVID kids had, and we held them accountable for it because that was your spring of your algebra year. We're going to ease you into more factoring, but we're at the point now where we expect you to know how to simplify radicals, and no more instruction on that. If you don't get that, come see me, talk to me. I'll be happy to explain it more. But as far as we're concerned, we've covered that review. This factoring, we're going to come back and circle back to when we get to a stinger and talk about reviewing that next time. So that video in this worksheet, thumbs up if you know what I'm talking about and we're done with that. Okay, Lila, you with me? Okay. Next up was the notes that you were supposed to do. So some of the kids yesterday said, oh, we watched the video. Some said we didn't bother watching the video. We just tried to figure it out ourselves. We couldn't. We'll talk about this and go over it. So if you could take this note sheet out, that would be perfect. If you need a copy of it, come get. If you're standing up to come get a copy and you also need a copy of today's homework, grab that too, because we're going to jump in and talk about 6-1. Before we do that, I want to talk to you about this midterm reviews to make sure that everybody is on the same page with what we're doing for the midterm. If you look at this schedule, you can see that your midterm is scheduled for February 16th and 17th. It'll be in class. A 40-question multiple choice test that'll count as half of your final exam. It's going to cover units 1 through 6. It's one of those conversations where we're not out to trick you, but geometry has too much content at the honors level to really cover adequately on a final exam. So what we do is we have the first half of the final at the midterm and the second half of the final in June. It's scheduled for 90 minutes. Our goal is to make it more of a 60 to 70 minute exam. So we come up with a test that takes us about 20-25 minutes, and that's how that math works out. So those 40 questions, kids like to know how many questions are on the test, and I always laugh at that because I tell them I could give you one question that takes you 10 minutes or 10 questions that take you 1 minute. right? So knowing the number of questions, how does that help? But for some reason, kids need that. Hey, we have set up on eCart 6 midterm review practice tests. And our expectation is for you working throughout the next couple weeks up until that midterm is for you to log on to eCart and do these eCart exams. If you're a person who needs assignments broken up into pieces as you go, we have Unit 1, Unit 2, 3 and 4, 5 and 6 spread out for you on our different assignment nights. But I'm not checking the eCarts until this day while you're taking the exam. So if you do Units 1, 2, and 3 tonight, rock on. If you do Units 1, 2, and 3 here and 5 and 6 here, rock on. But you have to get all 6 of them done. Does that make sense to you? They're each 10 questions, so your score on them will count as a quiz score. You have an infinite number of tries, so theoretically, everyone has the potential to get a 60 out of 60 for a quiz score. Make sense? Those eCarts should be available on your eCart. Has anybody already checked? Has anybody already, Cadence, were they there? Yeah, okay. If there's ever anything wrong with the eCarts, you can't get in, you don't see your score, it's like 20 clicks, and if I don't get all 20 clicks exactly right, then something goes screwy. Just send me an email, let me know, hey, this isn't right, or I couldn't retake it, or I didn't see my score. Reach out to me and let me know, because that's sometimes an easy fix for me. I just missed a click. So if you ever are getting into it and you're like, this doesn't seem right, shoot me a quick email and I'll be sure to get back to you and fix it. Sound okay? Questions on the eCarts, questions on the midterm, questions on the quiz that they're going to represent. Okay. So let's be clear about deadlines, because we've been struggling with getting things in on time. There will be 0 exceptions for these deadlines. So once I go through, while you're taking your midterm exam on February 17th, I'm going to go through and grade the eCarts. Here's why I need to make this absolute. Because if you go back, and let's say you get an 8 out of 10, and you're like, I think I can do better. If you go back and do a 9 out of 10 test, I don't know that you've updated it. It doesn't send me an alert. It doesn't let me know. So if you think about this, so I've got 90 Geometry Honors kids, and all of you are taking 6 quizzes. So that's 540 scores that I need to record. If you arbitrarily ask me to go back and check 1 or 2 different of your scores, it is a grading and data nightmare for me. Does that make sense to you? So I'm not doing it. So if you go back and update anything after this date, I won't see it. That's for your own educational benefit. You're welcome to, but it won't be a part of my grade. Does that make sense to you? It's got to be a hard and fast deadline, because it's not realistic for me to go back and check 90 kids and 6 different quizzes and to check in with whether or not they did a better job the second time around. Does that make sense? So the question a kid always asks is, what happens if I got a 9 out of 10 and I tried for the 10 out of 10 and I ended up with a 7 out of 10? I don't know. I'm assuming your last score is the one I see. So if you do worse, then take it again and do better. That's all I can say. Check in with your group, and right now make sure everybody understands about the deadline and the scoring and the quiz. Talk about it. Go. All right, so in 6.1 we started talking about using properties of proportions and started talking about ratios. I gotta be honest with you, ratios and proportions is truly my favorite math content to teach because it's so applicable to real life. And kids care about ratios and proportions, especially when it has to do with their grades. So every time that we tell you what one of your grades is, that's a ratio. Anytime you're comparing two numbers using division, you are finding a relationship between those two values. If I were to tell you I have 8 of something, or if you tell your mom you got 8 on the quiz, is your mom going to be excited about you coming home and saying, I got 8? What is she going to ask you? Out of what? I got 8 out of 8 on the quiz. What is she doing? 8 out of 10. 8 out of 20? Right? So that denominator tells a pretty big part of the story. Right? So when we talk about our ratios, the first thing we want to make sure that we understand is the numerator and the denominator. Okay. So we want to make sure that those two parts of our conversations are communicated. If I told you I have 8 of something, and I'm not talking about a quiz or a test, would you think it was a lot or a little? I have 8. $8. Not a lot, right? You'd be like, okay, well, you get a burrito. Can you still get a burrito at Chipotle for $8? Okay. So yeah, you can go get one deal, but like $8, not a lot, right? No. Are you texting to see if somebody wants 8? How much is a burrito at Chipotle? Right? What if I told you I had 8 dogs? That's a lot. That's a lot of paws to wipe and a lot of poop to pick up, right? So 8 dogs, no thank you, right? So your units, whenever we're talking about ratios or rates, that's a lot too. We want to make sure that we're understanding both the numerator and denominator. We want to make sure that we're understanding what it is that we're talking about. 2 kinds of ratios are part of our story. We can talk about part to part or part to whole. Part to part ratios are usually written with a colon. Part to whole ratios are usually written as a fraction, but you can write either one as long as you include units and everybody knows what you're talking about. Our percentages are our world's common denominator. When we put things out of 100, we suddenly make it so that everybody understands. So one of the famous jokes that Yogi Berra, I don't know if you know who he is an old baseball player that was kind of known for his wit. He would call up the pizza place and he would order pizza and he would say, yeah, but I'm not that hungry. Cut it into 6 pieces instead of 8. Which is actually kind of silly. Because if you're not hungry, you should cut the pizza into like smaller pieces, right? So go ahead, cut it into 10ths. Cut it into 16ths. Cut it into 12ths. I'll just have a piece. So that value of that denominator matters, right? But if you understand something out of 100, if you went home and instead of telling your mom you got 8 on the quiz, what if you told your mom that you got a 94 on the quiz? She's going to immediately associate that with percent, right? So that percentage is our world's common denominator. So if you watched the video or you did this, you went ahead and experimented and played around with the girls' soccer team, won 10, lost 2. The boys won 12, lost 3. So it looks like the boys lost more games. But did it actually turn out the boys had a higher winning ratio? Right? Because when you looked at the comparisons between the numbers. When we're talking about simplifying ratios, we want to make sure that we understand that concept of factors and what can and cannot be canceled out. So when we look at a number like 14, when you're looking at this, you need to see this as 2 times 7 times A times B times C. And in our denominator, you need to see this as 2 times B times B. Whenever we're simplifying ratios, anytime we have the same value in both the numerator and the denominator, that actually makes a fraction that's worth 1. So if we talk about what this is saying, can you go ahead and multiply 2 by 7 by A by B by C, and then divide it by 2, divide it by B, divide it by B, and you're like, okay, well, why would I multiply if I know I'm about to divide? So if we kind of break down our factors, then I can see that 2 over 2 is 1, the same as B over B is 1, leaving me with a 7 times A times C over B. So when I go to simplify, what I'm doing is any factor that exists above and below that fraction bar, it's a waste of my time to multiply it and then divide it. That's like untying and tying your shoes. It's a waste of your time unless that's what you're practicing. When we talk about factoring a quadratic trinomial, these factors are things that exist as part of a multiplication problem. In your spring of Algebra 1, you should have studied quadratic trinomials. Quadratic because of the 2, trinomial because of the 1, 2, 3 terms. I can break down a quadratic trinomial by unfoiling it. So I know if I have to multiply these together, it's x times x, x times negative 2, 4 times x, and 4 times negative 2. If I'm given a quadratic trinomial, I know that that's the product, or potentially the product of factors, and I can break it back down. So x times x is x squared, so I can take x squared, split my x's. I know that my factors of 8 are 1 and 8 and 2 and 4. My commutative property has me do 4 and 2 and 8 and 1, but it's silly to consider that or write that down. If I'm trying to figure out what two numbers are going to give me negative 8, I know one has to be positive and one has to be negative. This 2x is their sum, so I know my 4 is positive, my 2 is negative because 4x plus negative 2x is positive 2x. What you now notice is I again have factors above and below the fraction bar that are identical and can be canceled out. So if I'm given the factors, I can cancel them out. I can break down things that are already multiplied and look for common factors that can be simplified, because for this answer, what we're looking for is that is worth 4. You could write 4 over 1, but simplifying it completely puts it at 4. We want to make sure you understand about your units and the unit analysis. And if you notice, this is in days and this is in hours. And you're going to have a quiz on this, not next class because that's our cell day, but the class after that, next Thursday. And the biggest mistake for this one would be that somebody would call this, they'll simplify it, and somebody's going to say, oh, that's 1/2. Now, don't write that down because that's wrong. So it's not 1/2, because even though 5/10 simplifies to 1/2, I still have to take into consideration my units. And I need to do what we call a unit conversion. And I need to understand how to simplify this by understanding each of these units. I know that there are 24 hours in one day. 24 hours to 1 day is worth 1. If I multiply that times my fraction, I'm not changing its value. Just the same as you find equivalent fractions when you are looking for common denominators. But what ends up happening here is my units, days and days cancel. my units, hours, and hours cancel, and now I'm looking at everything on the same level. Now I can go ahead and cancel out things. I know that 5 comes out of 5 once and 5 comes out of 10 twice. And I know if I simplify 24 divided by 2, that is equal to 12. So the correct answer here, if you're asked to simplify, is 12, not 1/2. So there are a couple conversion factors that we expect you guys to be able to know. When we're talking about the metric system, in 1 kilogram, there are 1,000 grams. And I know that grams goes in my numerator because I need these units to cancel out. So if I want to then look at how I'm going to divide this, I've got 16 times 1,000 over 800. Now, however you go about simplifying that is up to you. I sometimes like to break this apart and call this 8 times 100 because I can make my 8 and my 16 friendly. And 100 comes out of 1,000 10 times. So I get a value of not 200, 20. All right, with your group mates, talk about what the conversion factor is for this guy and talk about the conversion factor for this guy. On your mark, set, go. All right, if you come back, you can see that in 1 yard, there's 3 feet. And I know which one to put in my numerator denominator because I know which ones I want to divide out and cancel out. This 5280 is, for some reason, my brain can remember 5 tomatoes, but it can't remember 5,280. So that comic cracked me up. If you look here, you can see he's got his America red, white, and blue stars and stripes on. And I don't know which country this is supposed to be. I'm assuming she's European. When I was in 6th grade, so that was 41 years ago. When I was in 6th grade, there's a huge national push where they wanted all of America to convert to the metric system. So they started changing the signs on the highway to how many kilometers until your exit. They started to rework everything. And we existed in this fumbling, bumbling limbo of ignorance because nobody knew the temperature because suddenly it was Celsius degrees. We didn't know what to wear. I mean, like, we didn't know how to weigh anything. We didn't. And America, in its most stubborn sense, as a population, we dug our heels in and said a big no thank you. We prefer our system that makes absolutely no sense. And they literally gave up. So I can't imagine how much money was invested in getting Americans to switch over because I know in my 6th grade class it became part of our curriculum where we had to start learning about the metric system, and they held it over our heads like, you're going to need to know this because the standard system is going away. And they threatened us and they made us learn it and we promptly forgot it. So we're holding on tight to our feet and our yards and our miles because Americans are stubborn like that. Any questions on the unit conversions? Go ahead. So the answer here is 12 no matter what. Yeah. So it's not 12 hours or 12 days. The ratio is a 12 to 1. So the story of this to that. And what ends up happening is Because you cancel out your units, you have no units.
Oh, okay, so it was fine, that we did it right.
Yeah, you did it right. As long as you ended up with 12, the ratio is 12 to 1. Okay? All right. So the next part of this lesson is where you practice with proportions. And understanding how all these properties work is really going to make life easier for you down the road. A proportion is a ratio set equal to each other. Your first and last parts of the proportion are your extremes. Your middle parts are your means. When we talk about cross products as our first property of proportions, I want to make sure that you understand it's not some kind of magic trick. It's not a party trick. It's not like you're saying, oh, just multiply across the equal sign and you'll get the right answer. That is true in summary, but not true why we do it. If you think about it, we can justify cross products. If I have A over B is equal to C over D, my multiplication property of equality says I'm allowed to multiply each side by B. You don't have to write this down, just take a look at it and understand how it works. Do you see how my B's then cancel out and I wind up with A is equal to C times B over D? Everybody okay with that? Notice I can do the same thing here by multiplying D over 1 times both sides. Do you see then I get A times D and these D's cancel out and I have B times C? So this cross products multiplying across the equal sign is a shortcut to multiplying each side by whatever was in the denominator of the fraction and canceling it out. As mathematicians, we always want the better, smarter, faster, easier, more efficient way of doing something. So we memorize, oh, this answer ends up just being these cross products. But don't think that that's some kind of magic trick that we made up. There's math that supports it. So when we talk about each of these properties, the reciprocal property means that I can take this entire fraction and I can flip it and still get a true story. And this is what's the most important thing that you have to know. If I flip 2/3, I get 3/2. If I flip 4/6, I get 6/4. Now, please understand, this is a true proportion, that's a true proportion, but they are not the same. Nobody said that they were equal. This is a story about two things smaller than one. This is a story about two things larger than one. So I flip it, I get a true story, but not the same story. Are you okay with that? When I talk about switching my means and my extremes, that means that if I switch B and C, or if I switch A and D, I'm going to still get the same values. And checking it out in numerical examples verifies the fact that you get true stories no matter what. I'm multiplying 2 and 6 and 3 and 4 each time. But nobody says any of these proportions are equal. Understand the difference between equal and true. This one is the coolest one to talk about because when I talk about my adding 1 proportion, if you back this up and look at your step that happens before this, you know that if I had A over B plus B over B, because these two have the same denominator, I can call that A plus B over B. If I have C over D plus D over D, I can simplify that by saying, oh, that's C plus D over D because they have a common denominator. This property, what we care about is this value here is a value of 1. So my addition property of equality says you're allowed to add 1 to both sides of an equation without upsetting the balance. So if this is a true story, then so is this, because I've added 1 to each side. The next property that you are supposed to know is our geometric mean. And that's going to be these two numbers that exist in this relationship. And here's where we end up practicing lots of simplifying radicals. Because every time I want to solve for the geometric mean, I got to take the square root of the product of those values. We're also going to talk about extended ratios, where we have ratios that exist of more than two terms. So if you want more explanation on any of this stuff, go back and watch the videos posted on Schoology. At your table group, you have a key to 6-1. So go ahead and scan through yours, compare it to mine, ask me questions on any things you don't understand. When I look at 1, 2, and 3, the most important thing that I can think of to make sure you understand is how you have to bubble wrap expressions, putting them inside parentheses, and using your distributive property here and here, making sure you have the distributive property. This problem here shows my geometric mean. Now the key that you have is a little bit different from mine, just because that's Mr. Logan's key. He made extra copies, so I took them. If you need help with the conversations about setting up the ratios or solving them, please let me know. This problem here with the buildings ends up being a geometric mean problem because the height of the building is the same as the width of the second one, and I do end up simplifying those radicals. The school picture example is one of my favorites because it's so very true. A lot of times they'll give you a picture as a 4x6 and you'll go to spend all your money. True story, this actually happened. I looked at the 4x6 proof and I liked the picture, so I bought it of my kids. But I wanted a big one to hang on the wall. So I ordered it in an 8x10. And all of my kids' heads were cut off. So, right? I was so pissed because I was like, I spent all that money on this nice picture to hang on my wall, and it was a perfect picture when it was a 4x6. But then I get the portraits in the mail, and they're missing their heads, and I'm like, what the heck? And then I thought about it. I'm like, all right, Tracy, for a math teacher, you're pretty stupid because everybody knows a 4x6, if they blow it up into an 8x12, would be in proportion, but those 2 inches was where I lost all my kids' heads. The funnier thing is if you try to deal with a 2.5x3.5, those wallet sizes, my kids always end up, I'm missing half of their faces. Because this is in proportion with a 5x7, but not a 4x6. It's different ratios. All right, 3 different ways to solve this popcorn problem. Take a look at Mr. Logan's key. He wrote a 2x plus 3x has to be equal to 25. X is going to be whatever factor. But think about doubling or tripling a recipe. So that X is that factor that you're doing things by. For me, I set up a proportion. If 2 to 3 is going to be X to Y. Here is it's solved as a system of equations. I know the sum of my parts has to be 25. And I went ahead and substituted in and solved to get my 10 cups of oil. Here is a conversation if you just want to try to make a table. So if this is the original proportion, this is if I double the recipe, this is if I triple the recipe, this is if I multiply 4 times, this is 5 times, and each of these I can add together until I get to 25. Any one of those methods of solving that is good math. When you think about having that X as a factor, if I know the perimeter is 18, then each of these is the simplified ratios of my sides of my triangle. And I know that that means that my ratio was simplified by a factor of 2. So I didn't have a 1 and a 3 and a 5. I actually had a 2 and a 6 and a 10. So the interesting thing is when the kids from the other class was like, well, couldn't you just add these together? 1 plus 3 is 4, plus 5 is 9. And because I know that 9 and 18 are separated by a factor of 2, could I have done it that way? Absolutely. 11, testing your properties of proportions. You want to make sure that your cross products are true. So if this is my initial proportion, 11n is going to be equal to 7n. Notice that ends up happening each time. This is equal to 1. So I can subtract that from your side. This is the one that's wrong. I need 11m. So D was wrong on that one. Given this diagram, I can substitute those values. And then we can talk about matchbox cars. So matchbox cars are so very cool. I don't know if you guys have ever played with matchbox cars. I'm assuming the answer is yes. But matchbox cars are different from Hot Wheels because matchbox cars are actual replicas of real life cars. Hot Wheels cars are made up. So they just design a really cool car, mass produce it, and call it done. But matchbox cars are based upon real life cars. So if you take my matchbox cars and share with the different cars in your group. If you look underneath the matchbox car, if you look underneath the matchbox car, every single one of them has a ratio underneath the car. Some of them are easier to see than others. But talk in your groups and see if you can find this ratio. Like this one is 1 to 52. So when I look at my two cars, this one has a ratio of 1 to 52. That means that for every 1 unit here, I need 52 units here from this scale model to the real life model. This guy here, I think is the biggest one, and he has a ratio of 1 to 114. But the interesting thing is, if you look at these cars, they're pretty much the same length. They're pretty much the same length, about 8 centimeters, about a little bit more than 3 inches. So the interesting thing is, they're all scale models, but not even close to being the same. There's no way that if I was sitting in my little convertible here and I pulled up next to this command center, if I'm at the stoplight, there's no way that these two cars are remotely, let me turn them right side up. If I'm sitting at the stoplight, there's no way that me sitting in my car works with this command center. And these ratios help tell that story. Who can tell me how or why? Talk to me about what you think about the different ratios. What do you think, Stephen? Yeah. So in Matchbox world, and my kids were huge Matchbox car kits. Anybody? Huge Matchbox car kit? Like, they all, like, all of them, love to play with them. We had these special carriers that had baskets in them, where you would put the car in the basket, and then they had like this thing that opened up and you could stack all your baskets in, so that everywhere we went, we were carrying our cars, because that was a guaranteed way to keep the kids happy. They loved it. Playing with the lines on the sofa, or we would take painter's tape and make lines for them to make little neighborhoods and cities. Like the Matchbox cars, guaranteed easy, fun toy to travel with. Little kids' hands. Those cars have to fit in your hands. Those cars have to fit in the basket. No way are these two things the same size in real life. That's why there's such different ratios. This one is so much bigger. Almost twice as big, right? Then this one. This one's twice as big than this one in real life, right? And those ratios help tell that story. So my father-in-law has, he's the original owner of a 64 and a half Mustang. And he bought it when he was 18 years old with the money he made pumping gas, and was so excited his dad took him to go buy his first car. And he's had that car ever since, and it goes on display in the Mustang Museum at Hershey. There's a car museum in Hershey, Pennsylvania, and so they have leased or borrowed a couple of his cars to put on display in the museum. I don't know if you've ever seen them, they're like on loan from. So then the Matchbox company reached out to him and asked him if they could use his car. So if you ever see a 64 and a half Matchbox car, that car exists because they took all the measurements off of his car. So they put that car with laser measurements, recorded it, and then that's how they ended up with the scale model. By scaling it down. So everything is exact. The steering wheel, the size of the seats, the dashboard, the wheels, the hood, the windows, every part of that car is exactly a perfect scale model. Kind of cool to think about, right? What are your thoughts about this scale model? How do you think I can figure out if this is a true scale model or what I got here? What could I do? Yeah, I could go ahead and measure this. I could measure its width. I could measure its height. I could measure this width and this height, and I could see. How many times bigger do you predict this is than this?
50.
Yeah? Here's 1, 2, 3. What do you think?
16.
I'm going to go with 3.5. Let's talk about this way. If I have 1, 2, 3, how am I doing with 3.5? It's pretty good, right? So I would say, when we're talking about scale factors, this is 3.5 times bigger than this. It's a pretty accurate conversation about scale models. And if we don't do things according to the scale, then we end up having that distorted or that warped conversation. All right, any questions on the homework that you want to talk about? Yes or no? All right, so in 6.2, we're taking what we know about proportions and ratios, and we're applying it to polygons. So we had congruent polygons and triangles, meaning same size, same shape. Now what we're proving and talking about is similar triangles, where we know that they're going to have the same shape, but not necessarily the same size. The sizes of similar polygons are going to be proportional. And that proportion can be represented by a scale factor. So we'll talk about this when we get back.